How can mimicking the human brain revolutionize AI? Well, here we are in 2025, and the field of neuromorphic computing poised to redefine the landscape of AI and signal processing, offering unparalleled efficiency and autonomy. That's the big sales pitch. But what is it? What does it mean? I want to talk about it in a language that everyone can understand. So when somebody mentions the word neuromorphic computing, they don't talk like Doc Brown in Back to the Future thinking, great Scott. So I've invited Sumeet Kumar, CEO of a company called Innatera, and they're a company leading the charge with its groundbreaking spiking neuroprocessor, or SNP T1. And I wanted to learn more about how this year could be the tipping point for the commercialization of neuromorphic processors, and how this technology bridges the gap between biological brains and artificial intelligence. Cool, right? Yep, from wearable and IoT automotive applications. Their innovation is setting the stage for a future where devices can think faster, work smarter, and most importantly of all, in a world where we're taking sustainability much more seriously now, it consumes less energy. So what does all this mean? What does the evolution mean for the future of AI, and how will it shape the next wave of intelligent, energy-efficient devices? Well, let's dive in with my guest right now and discover how neuromorphic processing could transform the way we think about computing and connectivity. So a massive warm welcome to the show. Can you tell everyone listening a little about who you are and what you do?
Sure. My name is Sumeet. I'm one of the co-founders of Innatera, and I serve as the company CEO. My own background is in microprocessor design, and in 2018, we spun Innatera out of the Delft University of Technology here in the Netherlands, basically to commercialize this very new piece of technology that we had built, mimicking how the brain processes information. And this is basically the chip that we've been developing at the company since 2018.
And you're working in an incredibly exciting space. And one of the things I try and do on this podcast every single day is demystify some of these tech trends that we're hearing about, put them in a language everyone can understand. And I would imagine there would be a lot of people listening that are or have not heard of neuromorphic computing, and it has been gaining momentum. So I think you described 2025 is going to be the tipping point for its commercialization. So can you just demystify, tell everyone listening what it is and some of those key factors that you think are driving this shift and why the timing is right for scaling these processes now? And I appreciate there's about 3 or 4 different questions in there, but can you set the scene for us?
Absolutely. So just to start things off, neuromorphic computing basically means brain-inspired or brain-like computing. And the entire idea of this paradigm is that we develop computing solutions that work just like your brain. So, for instance, every time you see something, smell something, hear something, there are certain processes that occur in your brain that allow you to very robustly and very quickly identify what's happening in the world around you. And when you think about it, the brain is tremendously efficient. It's very quick. It's doing so many different processing tasks all at the same time. And I think that this is really the big ambition or the big goal for everyone in the computing industry. How can we create processors? How can we create computers that mimic the amazing capabilities of the brain and hopefully make devices which last longer in terms of their battery life, are more responsive, and more intuitively understand what it is that you want to do? That's what we do at Innatera. We build brain-like microprocessor, and we apply these processors towards finding patterns in data that comes out of sensors. Our chips tend to be about 10,000 times more efficient than conventional chips that you find in the market today. And essentially, they allow you to find patterns in sensor data while using 500 times lesser energy than conventional solutions. And they allow you to do that about 100 times faster. And the key to how we're able to do this is we use software that is inspired by how your brain works. And we have a silicon structure which closely resembles how your brain itself is constructed from the ground up. Now, in the last 10 years or so, you've seen so many more AI. So AI tends to be the big buzzword in the industry today. And I think that in the last 10 years, the industry has come a long way in figuring out how to apply AI and where to apply AI in the overall solution space that exists. And in the data center, I think that we've been very successful already deploying AI, and consequently, you see AI-based services popping up in the cloud all the time. But a fundamental gap that still exists inside the industry today is much of the data that is captured and sent to the cloud comes in from sensors inside of small devices like your smartwatch, your mobile phone, or the video doorbell, which is hanging out in front of your door. And today, anytime you need to do meaningful AI-based processing of the sensor data, you've got to capture all of that data from the sensors, beam that up over a wireless link over the internet to the cloud. And that's where you end up finally doing the processing, which is tremendously wasteful if you think about it, because a majority of data that comes out of sensors is actually just a waste. You throw it away. So essentially, the entire objective with neuromorphic computing that we think is going to be very powerful is that it's going to allow sensor data to be processed directly at the source itself. So as soon as the data comes out of the sensor, you're able to figure out if or not it's relevant and what's actually inside of that data. And then you can decide whether you want to send it up to the cloud, or you can actually implement a lot of application functions directly next to the sensor without ever even having to use the cloud. I think that's why neuromorphic computing is becoming so relevant today, because if you look out at the market, you see sensor-based devices popping up in such large volumes. There are 4 billion new devices coming online each year, and these devices tend to be packed with dozens of sensors, and you've got to process that sensor data in some way. And neuromorphic computing is increasingly being viewed as the most energy efficient way to process all of this data directly next to the sensor. And it's taken a while for the industry to really discover applications for it, but this is the reason why we think that the coming year and the years ahead would be very pivotal for neuromorphic computing as well as companies like Innatera, because we see a lot of applications taking off where neuromorphic computing is the key enabling technology.
And before you came on the podcast today, I was reading about Innatera's spiking neural processor, the SNP, I think it's T1, and how it's positioned as a groundbreaking innovation in the field of neuromorphic processing. But for everybody listening, a lot of people may have heard of NPUs in some of those new AI PCs, but how does your processor differ from those traditional AI chips and its advantages in terms of things like energy efficiency, real-time decision-making, and all that real-world stuff?
Certainly. So, to show you this spiking neural processor team inside of its evaluation kit, and we started providing this to customers in 2024. The T1 is the world's first neuromorphic microcontroller, which brings ultra-low power AI capabilities directly to the sensor. The T1 is the world's first chip of its kind that applies this brain-inspired processing technique that is based on something called a spiking neural network. What differentiates a spiking neural network from a traditional neural network is that spiking neural networks, which you find in your brain, have a natural notion of time built into it. They aren't these huge trillion parameter models, so to speak. If you look at spiking neural networks inside the brain for different applications like detecting certain sounds, they're very compact neural networks which fire in a very sparse way. They activate in a very sparse way, and they tend to be extremely energy efficient. And we think that these spiking neural networks are a great match for sensors because they allow sensor data to be processed very efficiently. Sensors tend to be very resource constrained because they've got to be very small and power efficient. And these spiking neural networks allow this processing to be done in a very efficient way directly next to the sensor. The T1 is perhaps the most efficient chip of its kind that can run these spiking neural networks in a native fashion in silicon. So for most applications, when you connect the T1 chip to a sensor, and when you're trying to do something like voice recognition, or you're trying to identify if there's a person standing in front of your door, based on a radar sensor, which has been integrated into the video doorbell, we're able to do all of this processing using less than a milliwatt of power, which is ridiculously low. And we're able to do that across complex applications. And all of this energy efficiency comes purely from the fact that the chips mimic the brain. They have a very power efficient analog mixed signal architecture that closely resembles how the neurons and synapses of your brain are structured and how they work together. And these chips run software which are based on spiking neural networks, again, the software of the brain, allowing them to be super efficient, super quick, finding patterns in sensor data. And this is basically a piece of technology that we've protected with about 19 plus patent families, so about 120 plus individual patent applications as of today. And that's really what sets us apart in the industry.
And one of the big promises of neuromorphic computing is this ability to bridge the gap between our biological brains and artificial intelligence. So how does this technology simulate brain-like neurons? What does it mean for the future of AI and computing? It feels incredibly exciting here. And where's this heading?
If you really drill down into how the neurons and the synapses of your brain work, and I'm really oversimplifying this to a very basic fundamental, is that these neurons and synapses have a notion of time built in. So rather than having 32 bits of data and 64 bits of data streaming through the processor, the neurons of your brain just use very simple voltage spikes. So when data comes in, the data gets converted into a pattern of spikes. And these spikes are separated in time. And what the neural networks in your brain does is really try to identify which of these spikes are correlated. And by finding those correlations, they identify patterns inside of the input data. So if you look at really how the neurons work, they're very simple structures. They collect charge over time. And when the charge reaches a certain level, the neurons fire an event. And that's all the computation there is inside of these neurons and synapses of the brain. And that's what our chips do as well. They very closely mimic the structure, and that's what allows them to be super efficient. Now, what makes these neuromorphic processors such a great match for AI at the sensor is that, first of all, they allow you to work with the sensor directly in the analog domain. So you don't really have to convert the data coming out of the sensors into a digital domain where you end up spending a lot of energy. You can actually ingest data directly in the analog domain. You can ingest that data as quickly as it's coming out of the sensor. So you remove a lot of the inefficiency in the pipeline between the sensor and the processor as it exists today. And then you're able to do really powerful AI right as the first step of the processing pipeline, which is something that is simply impossible to do today with traditional technologies. That is the promise of what neuromorphic computing is able to do right now. But looking forward, there are a whole bunch exciting paths for us to follow. And let me paint out what a couple of those really look like for you. One of those paths is really think about processors that are able to compensate for changing behavior in the system over time. So think about sensors that, over their lifetime kind of change how they behave. Either because they're starting to wear out, or quality changes, or they degrade over their lifetime. Neuromorphic processors are able to really compensate for all of this because they're able to learn on the fly. That learning is a very important feature as well, and that could be a completely separate direction in which we go, where these chips are able to learn in the field from data which they're ingesting constantly. Think about your brain. Your brain doesn't have a separate training algorithm and a separate sort of inference phase. Everything seems to happen in the same fabric at the same time. And this could be really powerful. Think about neural networks that can adapt their functionality over time, that tend to strengthen certain pathways as you use certain features and tend to weaken pathways as you don't use certain features. These are capabilities that these chips will be able to bring in. And finally, I think one very critical part of neuromorphic is really control. Think about yourself dancing, how smoothly you're able to dance or how well you're able to balance on a bicycle. And all of this comes down to your brain being able to process data in this low latency fashion, responding very quickly to the stimuli that you're getting in. I think neuromorphic computing will be very fundamental in driving the next generation of industrial automation, robotics, and general machinery with this sort of intelligence built directly into devices. So it's a very exciting future for neuromorphic. We're just scratching the surface in terms of the applications that we're able to do today.
And I'm glad you mentioned that, because neuromorphic processors are being hailed for their potential to revolutionize things like edge applications, from wearables to industrial IoT. And there'll be a lot of business leaders listening thinking about the ROI on any tech investment and what problems we're solving here. So how do you see this technology transforming industries? And are there any challenges that you need to overcome for widespread adoption? What are you seeing here? Because I would imagine you're setting off a few light bulb moments with business leaders at the moment. But again, what problems are you solving? What industries are you going after? And what kind of challenges do you need to overcome to get there?
So what we've seen in the last couple of years is a growing acknowledgement or recognition amongst vendors in the industry that are deploying sensors into applications that AI has a power problem. In deploying AI to many application use cases that we know of today, there is a significant problem that comes from the power usage of the microprocessors that are deployed into these use cases. And for a long time, the power problem was not really known to many practitioners within the field, simply because there weren't that many AI processors out there. But practically, we know now that the moment you try to do something at scale in the form of a product that you can deploy on the market, you end up consuming a lot of power. And that's the first place where we've been able to differentiate ourselves very well. Our chips basically consume, on average, under a milliwatt of power or a few milliwatts worth of power for even complex applications. And these are applications which run continuously, not necessarily applications where we're turning off the processor for a majority of the time, like many of our competitors do. And the value here has been incredible. And I'll give you a couple of examples of this. We applied our chips in a partnership that we did with a leading Japanese radar sensor vendor. And we applied the sensor as well as our processor towards video doorbells, basically as a way of identifying, without using a camera in the doorbell, is there somebody standing in front of your door? Because it turns out that when we turn the camera in the doorbell off, we're able to save a significant amount of battery charge inside of the device. And then you have to recharge the doorbell that much less. And we developed the world's most efficient solution for radar-based applied to video doorbells. Just to put it into perspective, our solution applied to a typical doorbell that you can buy on the market extends the battery life of the device by 6x. So rather than recharging the device once every 3 months, you end up recharging it once every 1.5 years, which is a radical increase in improvement in user experience. Think about, how often you've had to go and take the doorbell off of your door frame and then charge it overnight and then install it back again. You have to do that, once every few years with our technology inside. We also had a different use case where we applied the chips towards what's known as audio scene classification in headphones. And the idea there is that you're listening to music in your living room, and then you get up and you walk out the front door, and now you're in a noisy street, and then you get into a crowded bus. All of these environments have a radically different noise profile, and they kind of affect how you perceive music. And in order to cancel out the effect of all of these different noise profiles, the headphones have to pick different filter settings continuously based on where you are. But the key problem there is the headphones have to identify the environment that you're in. And once again, we had by far the most energy efficient audio scene classifier of its kind running on our chips with an accuracy that was top of the line, competitive with the rest of the industry, with a latency about 3 times shorter than what our closest competitors were able to do. But most importantly, with a power usage that was about 10 times lower than the most efficient microcontroller available in the market today. So very simply put, what we do for vendors, for OEMs and ODMs that build devices is that we allow groundbreaking new application functionalities to be realized wherever you're trying to use a sensor which is producing data. We allow that data to be processed very efficiently and very quickly, allowing you to unlock fundamentally new sensing use cases and sensing functionalities, even in devices that run on really tiny batteries or devices that require very fast response times. And this is something where we've been outperforming traditional AI-based solutions that have been available in the market for a few years. We're outperforming them by leaps and bounds.
And you mentioned the power problem there. Scalability and energy efficiency are long known for being critical for advancing AI. And you mentioned how you're addressing some of those challenges, but also what role do you see it playing in enabling a new generation of smart devices? Because again, it feels like there's some big opportunities here.
There are. Recently partnered with a different Belgian-American sensor vendor. And what was really spectacular here is that we were using a sensor type which has been around for a while, and where this vendor had been working on developing a very new class of application function to take to market, but it had simply not been possible. And then we came along, and in a span of 3 weeks, we had a first prototype of a really fundamentally new application, which we'll be unveiling in a couple of months from now. And this thing introduces radical new capabilities, the ability to detect human presence in different smart environments, even in devices that run on really tiny batteries. And this is really showing the way in some sense, giving us an idea that there are applications out there that we've simply not thought about yet, because the kind of AI capabilities that we have available to us, they're simply not suitable for many of these applications. And with the neuromorphic processors coming into the picture, there are so many new applications which are now made possible that even with the OEMs and ODMs that work with our chips, the realization is that this opens up a completely new class of application features that we've not even been able to, we've not even been thinking of so far, because we haven't had a tool to achieve these. These are suddenly made possible with your chips. And that's the kind of feedback that has been the most revealing. So to us, it kind of feels like you're inventing a completely new class of device, a completely new segment of the market with this technology, which so far has been completely untapped.
And traditional AI models have often relied on immense computing power, which has been limited for applications that require autonomy and speed. And just to allow everyone listening to maybe think bigger, can you just expand on how neuromorphic processing can almost redefine the possibilities for AI applications on the edge? Because again, it feels like the only limitation is your imagination, really. But how do you feel about this?
We think that it's a massive market with a huge impact. And I hope that it ends up touching all of our lives in the foreseeable future. There are billions of sensors sold every year. Like I said, 4 billion new devices, each with dozens of sensors inside. And our hypothesis is that all of these sensors producing data will need a processor sitting right at the front line, being able to filter out whether the data is relevant or not, if there's something of value inside of that data. And that's where neuromorphic processing is going to be of significant impact, whether it goes into a sensing function, a control function, a sort of a thinking function. Neuromorphic will eventually be everywhere, right next to the sensor. So you'll be touching billions of devices every year that have a neuromorphic component to them. And that's the kind of impact that we're looking at. One specific angle that excites me the most is how we can use neuromorphic for good. And there are 3 different aspects to this. The first is deploying neuromorphic in the context of human-machine interfaces. I think that human-machine interfaces can be a lot more intuitive. They can allow better access to technology for everyone. I think that this barrier between the physical world and the digital world should be much more intuitive for us to cross. And we're doing that with this notion of ambient intelligence, where the intelligence is around you, it serves you, it intuitively understands what you need to do, and you don't need to explicitly command it. And eventually that will lead to better access for technology to everyone. The second one is specifically around healthcare and quality of life. Something like a neuromorphic processor, by virtue of the fact that it's so energy efficient, could be sitting in your wristwatch looking at your heart rate throughout the day and picking up the first signs of heart disease years before you ever become symptomatic. So a little red light can go off in your watch and say, hey, I've just detected something potentially dangerous. You might want to go and see your doctor. And perhaps we could catch something long before it becomes fatal or while it is still treatable. And I think that this stands to revolutionize really how healthcare is implemented around the world, even in developing countries where you don't always have access to qualified first-hand diagnostics. This is perhaps an easy way to actually implement that across the board. And the last way is the entire energy crisis. We rarely talk about the cost of AI functionality in terms of carbon footprint. Do you ever think about how much your voice searches cost in terms of carbon dioxide emissions? You don't really think about when the face tagging function in your images, what the impact of all of that is. And today, much of that happens in the cloud. Some of that happens inside the devices in your hand. But there's a lot that we can improve in that process. So if you're able to streamline AI, if we're able to deal with more of the world's sensor data directly at the source, we can streamline how we use energy in implementing AI across the value chain. And we can make the picture a lot more efficient and a lot better. That's ultimately this three-part ambition that at least I have and that I would like to see personally. And that's what we're working, all of us at Innatera, towards.
And we're currently recording our conversation today at the very beginning of 2025, just before you fly out to CES in Vegas. So can you tell me a little bit more about that and ultimately how you envision the most significant industry, or what you see as the most significant industry shifts resulting from the commercialization of neuromorphic computing, and how are you preparing to lead this evolution? I would imagine CES is going to play a big stepping stone in that, but anything you can share around that?
Sure. CES is a really important show for us because one of our beachhead markets is the consumer electronics market, where we see a lot of interest ranging from devices like wearables and hearables down through portable devices like these battery-powered security cameras that you mount outside your house, or video doorbells, and even things like smart TVs and building automation systems. So there's really so many wonderful application use cases there that we're already targeting with some of our customers and partners with the chips. We have a very active event season coming up, so we'll be at the CES show at the beginning of January. And then we are exhibiting at the Venetian, and we have a number of our latest demos, really cool stuff on display. And I welcome you to come and see that in person. Some of this is really magnificent stuff, if even though I'm saying it myself. And we have more events coming up in March. We'll be at Mobile World Congress and Embedded World. And generally, most of our initial applications target the consumer IoT as well as industrial IoT verticals. We also have a number of engagements in the automotive space, because automotive is a very important area for neuromorphic. Think about the number of sensors that go into each vehicle and why energy efficiency is becoming so much more important in the context of future electric vehicles. And there's definitely a lot of work to be done in the automotive space as well. And eventually, we'll also have a bit more of a presence in that area. But today we focus quite a bit on the consumer space in terms of battery-powered devices, which is where I think our impact is the strongest today.
Well, hopefully we can bump into each other on the tech circuit at some stage. I am frequently taking this show on the road to various tech conferences around the world. But if I ask you to look beyond that, look into the future, look into a virtual crystal ball of sorts, how do you see neuromorphic computing reshaping our understanding of AI? And what role do you think it will play in enabling more human-like intelligence in machines? Because it feels like that's the next step. But how do you see this taking shape?
We've just taken our first chips into production. And like I said earlier on in the show, we're only scratching the surface in terms of the applications that neuromorphic processors are today. Some of that comes from the fact that we only have a limited understanding of how our brains work. We only have a limited understanding of the kind of things that your brain is able to do. And wherever we have these theories, it's still somewhat of a superficial sort of understanding where we can go a lot deeper. So from that perspective, I see neuromorphic processors being a completely new class of component within the computing landscape. Today, we're deploying them primarily for things like pattern recognition and sensor data processing, but I think there's scope for them to do so much more, learning and intelligence in new forms being applied across the value chain. I think that eventually neuromorphics will grow to take a good portion of that value chain in the future. But in exactly what form that is going to happen, I still don't know. Our ultimate ambition, I think by 2030, is to bring intelligence to 1 billion devices. And I think there's a lot more that's going to happen beyond that time frame. And it's an exciting time to be doing Neuromorphic just for that reason.
Well, we covered so much in our conversation today, and I suspect anybody attending CES will want to check you out in the Venetian. But for anyone that's not attending, want to find out more information, keep up to speed with some of the announcements that might be coming out of that, or just follow your progress throughout the year, where would you like to point everyone listening?
If you'd like to come and see us at one of the many shows that we do through the year, there's always an appointment booking page on our website that you can fill out. We'll get in touch with you. But our LinkedIn tends to have the most updates of what we're doing as a company and as a team. We tend to really have a people-first culture. So you see all the fun stuff that we do as an Innatera team here at the company. And we've got a bunch of new exciting announcements coming up, especially around our technology. So I hope you'll stay tuned on our LinkedIn. And we'll catch you at one of our events where you can see these things in person.
Fantastic. I will add links to everything so people can find you nice and easily. And I think for anybody listening that has heard about neuromorphic processes for the very first time, I'm hoping we've demystified it today, put it in a language everyone can understand why 2025 could be a tipping point and how it's bridging the gap between biological brains and AI, and ultimately what this evolution means for the future of AI, whether it be from scalability to energy efficiency and the future of smart devices. So many big things to take away and think about, but thank you for bringing it to light today.
Thank you so much, Neil. It was really great talking to you.
As we've heard from today's guest, the shift from traditional AI to brain-inspired neuromorphic computing isn't just a technological advancement. It's also a new way of thinking about how machines process information. And the spiking neural processor that we talked about today represents a big leap forward, enabling ultra-efficient, real-time decision-making for devices at the edge. And I think also by extending battery life, reducing energy consumption, or unlocking new AI capabilities, this innovation could shape industries and ultimately redefine possibilities. But as we look ahead, how might these advancements influence the way we design devices, interact with technology, and even address global challenges like sustainability? The conversation doesn't end here with this podcast episode as you go on to another episode or browse for information online. I want to know what questions you're going to be asking about neuromorphic computing, especially as it will continue to scale and evolve this year and beyond. As always, tech blog writer, outlook.com, X, LinkedIn, Instagram. I'm just at Neil C. Hughes. Nice and easy to find. So keep those thoughts, questions, pictures to come on the show coming over. Other than that, I'll be back again in your podcast feed, waiting patiently for you to hit the play button tomorrow. And hopefully you will join me there. But that's it for today. Bye for now.